Welcome back friends, good morning to all. Today again we will continue the chapter number 1. Friends, I am not a professor, I am not a lecturer, I am not a teacher, I am a self-learner. I want to share my knowledge to my juniors by self-study. This is the chapter number 1 we are continuing, and this is of my lecture 5th of introductions. So we will recap friends. Already what we covered, that general procedure in the machine designs, types of loads that we studied, the death load, live loads, the variable loads, impact loads, shock loads, like that we studied, and the stresses, two type, tensile stresses and compressive stresses also we studied. The stresses, when a material is subjected to a load, it will deform, and at the same time there is internal force will be developed that is equal and opposite to the applied forces, that will prevent the deformations. The internal force per unit area is called the stresses, and the strain change in the length by original length, that is called the strain. Unit of stresses, you know the force per unit area, so that is a Newton per mm square. You already discussed, and problems already we did. The shear stresses, when a force is acted tangentially, the stress is developed, that is called shear stresses, and corresponding strain is called the shear strains. That is shear stress and shear strain. Due to the shear stresses, the rivet has been become to two pieces. Okay, so shear modulus, the shear stress is directly proportional to shear strain within the elastic limit. That is called the shear modulus. If that is G or C, we are denoting by the C or D. And the bearing stresses is called localized compressive stresses. When a material is subjected to a loads, there will be localized compressive between the two matching parts. It is happening that localized compressive stress is not bearing stresses. Here you have to take the load divided by the projected area, and projected area you have to take, okay, the bearing stresses, and we did the some problems also we did. And last chapter also we covered the stress and strain diagram of the mild steel specimens. The mild steel specimens we studied. The mild steel specimens like this. So B, suppose C, this is D, and E and F, this is stress y-axis, and strain is x-axis. Okay, so the up to A, up to O to A is called proportional limit. Here stress is directly proportional to strain, and the elastic limit, if you load beyond the A and up to B, and if you remove the load at B, and it will come back to its original and shape size, that is called the B. And after B, if you loaded, then the plastic deformation will start. If you remove the load, it will not come back to point, that is called the yield point. And the yield point, what is happening is that without just little application of load, the strain will be there, more strain will be there. Lower yield point, at lower yield point, what will happen, there is a load, this will drop the loads to a points, and after the lower yield point, then it will regain the strength of the materials due to the strain adding effect up to E, or up to the E, the point E, that is called the ultimate stress. It will be largest stress or largest load taken by the materials. And breaking stress, after E, the necking will be formed, and it due to the resistance also will be dropped to the point and F, that is called the breaking stresses. And this is what already we discussed, just I made the recap. Okay, that is 5 points: proportional limit, elastic limit, yield upper and lower yield point, ultimate and breaking stresses. So friends, in this chapter, actually at the end of my lecture, the student will be able to understand what is the working stress. Already you discussed, but again I will tell you, and factor of safety, and the selection of the factor of safety, why you are taking the factor of safety is important. And we will see the, as per your syllabus, the mechanical property of the materials we have to cover, and we will cover what this is proper mechanical properties. You have to know as a designers what is the strength, the stiffness, elasticity, plasticity, ductility, brittleness, and malleability, and the toughness. machinability and resilience, creep, fatigue and hardness. This is some 13-point mechanical properties there. We will discuss each one by one. Friend, what is the factor of safety? Factor of safety is defined as the maximum stress to the working stresses, that is called the factor of safety. Suppose you are making this is the stress and the strain diagrams. Suppose the materials here you just see this is mild steel, you know, up to this point that is ultimate stresses, but this point is suppose this is A, this I will tell B, this will see C, and this is D, this is F and E and F. Suppose E, this is ultimate stresses will take, and this is you are taking the yield point, so YE will take. Okay. So what the factor of safety means? You always work at a stress which is below than maximum stresses, maximum load taken stresses or load taken by the member. Suppose the ultimate stress is 250 MPa, suppose MPa, you work a machine such that it should be lower than 250, then only the material will not fail. If you work more than 250, what will happen? The material strength itself is 250, but you working more than 250 means 260, 270, the material will fail. So always you keep in your reserve strength. So that is called reserve strength, or that is you called safety, factor of safety you keep, that is called reserve strength. Suppose I will work at a stresses, that stresses suppose stresses 100 MPa. So the load is such a that the load will act on the member such a that the stress will develop to only 100 MPa. So you know that load is equal to, stress is equal to load by area. So in that concern the stress will induce is 100 MPa. But the material, each material, so there is some strength there. That is called we call maximum stress taken by the member to divided by working or designs. So I will working or design strength is nothing but which is lower than the maximum stresses. Okay. So factor of safety you understood. The factor of safety is equal to maximum stresses can be the material can take. That may be the ultimate stresses you are taking sometimes, or you are taking the yield strength. So that is doesn't matter. But that should be less than the the stresses. So here what is factor of safety? Suppose I am taking the ultimate stresses. So ultimate stress is equal to 250 by the working stress is equal to 100. So how much is coming? 2.5. So the factor of safety always is greater than 1. It should be greater than work since the maximum stress is more. Okay. So friends, there are two materials already we know that one ductile material, one brittle material. The ductile material will apply the loads, it will be deformed, appreciable deformation will happen before the breaking. That is ductile material. Brittle material means what? It will fail without noticeable deformation. So brittle material it will fail by application of the load without noticeable deformation, means less deformation it will fail. So that we know that. And ductile material, where the yield point is not clear defined, the factor of safety is based on the yield strength. So what is happening? The material, the ductile material, it is the factor of safety is based on the, I told you. So you draw like this, the stress and strain diagrams. Suppose like this. So this is you know the yield point. Suppose I will make this is yield point. This is I will make the ultimate stress. Okay. You here what is come ductile material, where the yield point is very clear. His yield point is very clear. So friends, the failure of material is doesn't mean that it will be separate two pieces. It will fail when it is not functioning the satisfactory function. If you are not making, then we will tell the material will be fail. So here what after yield point, the ductile material, what is happening, that there is a plastic deformation start. The plastic deformation start itself will tell that this is a yield, that is called yield or the failure of the material. So here we will tell the ductile material the maximum stress we will tell yield stresses, and suppose yield stresses, suppose the yield stresses suppose 250 MPa, suppose yield stresses, we should work stresses that is called working stresses in working sigma W tell that I will tell 100 MPa. Then the factor of safety of the yield point we are taking, so 250, the factor of safety FOS is equal to yield stress is equal to 250 divided by 100. So like that you have to calculate. Okay. Sometimes you can take also the ultimate stresses also you can use. That time the plastic deformation is not important. That time ultimate stresses, the plasticity is also important. That time you can take the ultimate stress also. In case of a brittle material, the cast iron, suppose this is the cast iron stress and strain diagrams. So what is happening? It is failing like this. So here what is happening, that here there is no yield. The yield point is very difficult to identify. So that time we are using the 0.2% offset methods, right? Here ultimate stress is directly we are taking. So ultimate stress is equal to 100 MPa. Where the yield point is not well defined like ductile material, therefore factor of safety we are taking as a based on the ultimate stresses. So ultimate stresses, that ultimate stress is 200 where yield point is not and you take working stresses of sigma W is equal to, you take a 50 MPa. So you will see the factor of safety is equal to, in ductile material you are taking the ultimate stresses. The ductile material you are taking yield point and brittle material you are taking the ultimate stress. Here what is coming? 100 MPa divided by 50. So how much is coming? 2. So factor of safety is always greater than 1. You remember that. It is coming at exams, they are asking what is the factor of safety. Factor of safety is always greater than 1 because you are taking largest stress to the working stresses. Okay. So the relation is found in this one. The above relation factor of safety is used for the static loading. So this is depending upon the types of loading, based on the factor of safety you can decide it. So the maybe the dynamics loading, that is the factor of safety is different. In the static loading, that the factor of is different. So friends, why you are considering the factor of safety, that is very important. The factor of safety, see that is so many different factors is considering, that's why you are taking the factor of safety. Otherwise what is the working stresses is different, same as the maximum stresses, but in usual practice the strength of materials what you are calculating is not as for the this is depending upon different fabrication process, and also it is the types of load what we are applying. Always we are telling static load, and really that is a static load. There may be a part of suddenly you can increase the load. It is always not slowly you are applying the loads, and we are telling that this is the change of the property during the service condition. Always we are testing the materials at we are testing some materials at a different condition, but actually in service condition that the material is using in different service conditions. Some example I will tell you. Suppose you are material testing at UTM machine which is 25 degree centigrade room temperature you are testing, but you are using that material at a 40 degree and 50 degree outside atmosphere. Whether the property of the material will be same? No, it isn't, because the temperature is there, then again because the outside temperature is more, so that the property of the material will may change. But I given that actually the strength of material is equal to 100 MPa suppose, but outside it may be 80 MPa. But in that sun I cannot again bring the specimen, again I cannot test. So I can give the factor of safety, that's why suppose 100 is there, I will give factor. So 50 you can take, and outside you can work, that is not a problem in that condition. So it is different factors. I will tell you the reliability of the property of the materials and the change of this property during the service condition, because the service condition that we know, the hot and the cold condition, it will be service will change, we don't know. So based on this you have to take the considerations. Okay, this is the factors is affecting due to the service conditions. We have to calculate the factor of safety, or the reliability of the test results and accuracy of application of the results in actually in the machining practice. And I am doing the test results in the machine, but accuracy of same test condition you cannot apply the real in the practical is difficult. Test results you are testing at the test condition, you are testing at the lab, but you are actually applying the results in the actually machine. So machine involvement and the testing involvement and different. So in this condition you have to apply the factor of safety. Reliability of the applied load. So I told you different applied loads is there. the static loads and dynamics loads and impact loads, shock loads, and you should know the reliability. You are doing the test at gradually applied loads, but really it is in gradually applied load. There may be the frequency, or there may be the instead of gradually, there may be slowly, very slow, or maybe just more than the gradually applied loads. It may be the near to the impact loads. In that time also you have to take the factor of safety you have to consider. These are factors. It is make sure that you have to apply the factors of safety. Otherwise, all factor you cannot consider in the test condition. The extension of simply of assumption. You are assuming it is simple is isotropic, homogeneous isotropic materials. Whether the material is isotropic or homogeneous materials, no. So based on this, you have to give some little factors. Localized stress, we don't know that suppose the specimen is like this, but there is a maybe small discontinuity will be there. So localized, what will happen, the stress will be increased, but in that condition also you have to give the factor of safety. These factors is making forceful that you have to give the factor of safety. The extension of initial stress after during initially stresses set off during the manufacturing. In the manufacturing process, due to manufacturing, what will happen? The initial stress is set off during manufacturing. What is happening? There is also some stress will develop due to the processing. Okay, that is called the internal stresses also will develop during the manufacturing process. So we don't know all things to take into the consideration. Factor of safety is important. The extension of loss of life. Suppose suppose 100 life is important. To prevent the loss of the life, factor of safety is important. If I will give 100 kg of 100 MPa is the material strength, but if you will work 100 MPa, there is a chance of failure of material, and working the main levers, it may be the fail, suddenly it will fail, and people the life will be that is in loss of life, it will come to play. So in that condition, I should give the factor of safety. That's why such that suppose the 100 MPa is the material strength, so I will always give 2 or 4 it will give. So if you will give factor of safety 4, 100 divided by 4 is equal to 25 MPa. 25 MPa below will work, then it is a safest working environment, safest person, safest point. The extension of loss of property is the failure. So see, this is very important. Property is also important. So if you work maximum load, there is a collapse, then the entire cost of the material sheet is spoiled. So always you work below the ultimate stresses. So by the giving the factor of safety. Okay. So friends, this is the factor of safety. A different load, we are giving the different factor of safety. And this different material, we are giving the different factor of safety. I will give the cast iron. Cast iron we are giving 5 to 6 if it is a steady loads. If this is live or that is variable or dynamics loads, we are giving the 8 to 12 factor of safety. And if this is shock load, we suddenly shock load with a little time we are applying this loads shock, then that is 16 20. So whenever steady load, we are applying the less factor of safety. Whenever it is going the dynamic and shock loads, in that concern the factor of safety increase. That is the point to know. The wrought iron, it is 4 and the steel is 4. This is the steady loads, and the soft materials and alloys are giving 6, leather 9 and timber 7. Similar, it is a live loads is also a live load, it is increasing. Okay, 7, 8, 9, the wrought iron, steel and soft materials like that. And this is shocked, that wrought iron 10 to 15, steel 12 to 16, and soft metal that is 15. Similar things at live loads, leather is 12, but in this same cases it is shock load, that is 15. Timber, that is 7 is the steady factor of safety. Here the life is 10 to 15 and the same is 12. Just this is a glance that the factor of safety is increases as depending the factor of depending upon that type of load. It may be the steady or maybe the live loads or maybe the shock loads. You have to shock load the highest, remember that. Steady loads, the factor of safety is less. So friends, mechanical property of the material before you know, then just a glance I will tell that classification of engineering material I will just briefly I will give. The engineering materials are mainly classified with metal and the alloys such as iron, steel and copper, aluminum, and one another non-metal such as glass, rubber, plastic, etc. Okay. So, metal you know that iron and steel, copper and aluminum, these are metals. Non-metals like glass, rubber, plastic, this is all non-metals, and you can classify the metal and with the layer with suppose metal I classified metal. So metal with metal may be classified metal one non-metal. Okay, metal that is copper, aluminum, these are metals. Non-metals, that is rubber. Again metal will classified, one is a ferrous, one ferrous metal, one is a non-ferrous metal. Ferrous metal where the principal constitution is iron, then that is called ferrous metal. Which that principal constitution is not the iron, that is called non-ferrous metals. So the ferrous metal are those who have iron as their principal or main constitution, main constituent, main ingredient, okay, main materials. So what is this? You know the La. La is equal to, it is a combination of two more than two metals, then that is called the Ls. Okay. So if we tell the ferrous metals, okay, La, okay, if one of the suppose one metal is a combination of two metals, two constituent or two integrity, like iron is a constant of that is iron is a carbon, okay, and this suppose you are taking the irons, right? Iron is a combination of carbon and this Fe, okay, iron. Here principal constitution integrity is the iron, then that is called the ferrous metal. If the other than iron, iron is not the integrant of the metal, then that is called non-ferrous. Suppose in copper, copper is copper plus zinc, copper and aluminum, there is no iron integrant is there, so that is non-ferrous. And brass, that is copper plus zinc, and tin also zinc, etc. There is no iron at all. So in that La, so that is called non-ferrous metals. So one is ferrous metal, other is non-ferrous metal. Iron as their main constant, such as cast iron, wrought iron and steel. This iron is coming to pictures. So we are telling the steel, it is iron Fe plus C. C is carbon and Fe. So here the Fe iron is steel, Fe is coming to pictures. Fe means iron is coming to picture. That's why it is called ferrous metal. So wrought iron, that is iron and carbon also. Cast iron is more than 2% of the carbon, but it is iron is present, so that is ferrous metal. Here non-ferrous metal, metal other than the iron is iron will be not there. Metals other than iron as such as main integrant, such as copper and aluminum, brass, tin, zinc, it is called non-ferrous metals. So friends, this is the properties of materials. Property means this is characteristic of the metals. So there are different characteristics of material and different properties there. One we will see, this is one mechanical properties, one is chemical properties, one physical properties, four is technological properties. So mechanical property, it is called traction, compression, bending, brittleness, strength, ductility, elasticity and heat resistance and plastics. The impact, hardness, the Brindle, Rockwell and Vickers hardness, this is coming again the mechanical properties. If chemical properties such as corrosion, resistance, combustibility, toxicity and reactivity, that is coming chemical properties. Properties related to the chemical atmosphere, that is called chemical. Mechanical property related to the mechanical environment, the property is called mechanical. And similar physical properties, a melting point, density, thermal conductivity, specific heat, electrical resistivity and magnetic permeability. These are called the physical property. And the technological property like welding, machinability and malleability and castability. This is coming to the technological properties. Okay. But as per our syllabus, our interest is mechanical property. You have to see. So in mechanical property, we will see this in 13 properties. Okay. Strength, stiffness, elasticity, plasticity, ductility, brittleness, malleability, toughness, machinability, resilience, creep and fatigue and hardness. This 13 property we will see one by one. Okay. What is the strength? It is the ability of the material to resist the external applied forces without breaking or yielding. That is called strength. The internal resistance offered by parts to external forces is called stress. That is So what is that? It is the ability of the material to resist the external applied forces without a break. So the strength means, suppose that is the metal either will apply the load, suppose F, it should not break or it should not yield. Yield means the plastic deformation which should not be occur. So if you apply the load F, it should not, external forces were applying F externally, but it will not break. That is called the strength. Okay, that is the strength. But its strength is also sometimes is called the stress. You know that if you apply the loads, when a material is subjected to a loads externally, then it will deform. And same time the internal forces will be developed inside the body, which is equal and opposite to the applied forces, which prevent the deformation. The internal forces per unit area is called stresses, or that is called the intensity of the forces. Okay, so that is called the strength. Okay, if ability of material to resist the external applied forces without breaking, then that is called the yield. It should not break. What is the strength means? It should not be break or yield. That is called the strength. Strength may be the tensile strength either or compressive. If you apply the force is tensile nature, so it should not break during the tensile stress, then that is called the tensile strength. If applied force in the compressive nature, means equal to pull, then material should not be break or yield, that is called compressive. Like that, shear strength, crushing strength you can do. So tensile strength, this is the ability of the materials to withstand the tensile loads without rupturing or without the fracture or without the failures. The material is in tension. So this is the, if applying the external tensile loads, it is the materials and the FEG. So it should not be break or it should not be fracture. Then that is called the tensile strength. So compressive, if you apply the forces is in compressive natures. So the ability of the materials to withstand the compressive or squeezing load without being crushing or broken or withstand fail. This material is in compression. This is called the compressive strength. So shear strength, I told you, is the ability of material to withstand the offset or transfer loads without ruptures. So this rivet either you are applying F, it should not fail. Okay, the rivet connecting two bars shown in the shear wheels, the bar themselves are in the bars are tension, but the rivet is in subjected to the shear stresses. Okay, the bar is tension. Okay, note that the rivet could still be the shear if the bar is in compression. If you apply the compressive load also, the bar will be rivet will be the shear. What is the stiffness? It is the ability of material to resist the deformation under the stresses. So the stiffness is the ability of materials to resist the deformations under stresses. The modulus of elasticity is a measure of the stiffness. Stiffness, we are telling sometimes K. Okay, the stiffness is the resisting the deformation, that is the resisting to failures. By what is the stress? Strength is the resist to deformation, resist to fails. Okay, here the resisting to the deformation. Suppose I will tell, suppose this is the cantilever beam. You are applying the loads. What is happening? It will deform. It will deform. it will deform. Apply the load and it will deform. Deflections. So if you apply the load here like this, you are applying the load P, what will happen? It will deform like this. So deformation under stresses. So it is also, we can tell the stiffness is different from load per unit deflections. So stiffness K, we can the load per unit deflections. The ratio of load to deflection, that is called stiffness. So load is equal to Newton, deflection is equal to mm. So the unit of the stiffness is equal to P by deflections. So we can tell that it should not deflect, it should not deform, it will less deform by application of loads. If you apply the load, it will deform like this, the stiffness is less. If you apply the loads P, if it deflects less, then it will call the good stiff. The ability of materials to resist the deformation under the stresses. So what is happening, suppose in this case if you take, the deflection is equal to the deformation PL by AE. So if you see deflection by P is equal to L by AE. So if you make reciprocate P by deflection is equal to AE by L. P by deflection is nothing but K. K is equal to, the stiffness is equal to P by deflection. So K is equal to AE by L. So if you see, the K is proportional to E, and A and L, A is equal to the cross sectional area, L is equal to the length of the bar. So A and L is equal to very, very small as compared to the E. So E is equal to, you are telling modulus of elasticity of the, suppose mild steel available 210 GPa. So 10 to the power 9 Newton per meter square. So as compared to area and L, the E value is like. So if stiffness, so K if will increase, E is equal to, suppose increases, stiffness increases. So that's why the modulus of elasticity is a measure of the stiffness. Since the elastic modulus is depending upon the K value is depending. So if E is increasing, Young's modulus is increasing, then K is increasing. That is more stiff. Okay, that's why the stiffness is the ability of material to resist the deformation under application of the loads, okay, or stresses. Elasticity, you know already, it is the property of the materials to regain its original shape after deformation when external force is removed. This property is desired to material used in the tools and machines. For example, both mild steel and rubber are elastic, but the steel is more elastic than rubber. Remember that. You know that what is the elasticity? It is a property of the material by virtue of which, when we will apply the load on the members, it will deform. If you remove the loads, it will come back to its original shape and size. That property is called the elasticity. This is actually used in the tools and the machines. And if see, if you will take the one rubber piece, same area and length, if you will same area and length of one, this is suppose rubber, same of one mild steel if you will take rubber and same piece of same area, okay, and length is same. If you apply the loads, okay, the mild steel has, it will elongation of the mild steel is more as compared to the rubber. Elasticity of the elastic, it is more elastic. If you see the mild steel, this is the stress and strain diagram of mild steel. If you see the rubber, rubber is like this. This is rubber. So if you see the elastic range of that is less. It is more in mild steels, elastic. Here if you see the elastic range is very, very small. And if you see the rubber around, I think 10 GPa is the modulus of elasticity. It is seeing here is 210 GPa. So which is also the indication of the elasticity. And actually the rubber, the post elastic deformation is more. If you see here, the elastic, if what the rubber why is more elastic means, less elastic than mild steel means, suppose this is the elastic limit. After the elastic limit, okay, after the elastic limit, the plastic deformation of the rubber is more. Just see, this is suppose the elastic point of rubber. After elastic, post elastic deformation is more than the rubber. So that's why it is more elasticity. So remember that the elastic materials, mild steel has a more elastic than the rubber. They are asking that. Elasticity, you know that the ability of metal to deform under the loads and return to its original shape and size when the load is removed. Such material is used for the making the spring. So friends, if this is the, suppose this is spring materials, this is original before loading. If you load like this, then what will happen? It will deform. Okay. Then you will remove the load spring, again it will come back to its original shape. This is 1, okay. Position 2 and 3. The position of 1 is equal to position of 3. So it is come back after removing the loads. Then this type of material is property is called the elasticity, or material is called elastic materials. Plasticity is the reverse of the elasticity. The property of this is the property of the material which retain its deformation produced under the load permanently. So if you load, if you apply the loads, what will happen? It will deform. It will deform, and the deformation it will be retained even after removing the loads. Means the deformation, it will not come back to its original shape and size. That type of property of the material is called plasticity. Permanent deformation of materials, when the stresses exceed the yield points. You know that if the stress and strain of mild steel if you are taking, after the yield point, then the permanent deformation will start. That is means the yielding will happen. The property of material is necessary in the using the forging. Forging, what you are doing? Metal, you are hitting some temperatures. After that, you are putting the hammers and you are hitting, right? That is used in the plastic. And stamping of image, coins, when you are making the coins and ornamental works, in that times the plasticity is very important. Means it is the property of the materials which retain its deformations under the load permanently. Deformation is here permanently, but in elasticity the deformation is temporary. So I can tell plasticity, it is defined as it is property of the materials by virtue of the which if you apply the loads, it will deform, and the deformations, it will retain the deformation even after the removing of the loads. That property is called the plasticity. It is a permanent deformations. Okay, this property of material is necessary in forging and coining and ornamental works. So friends, the ductility it is a property of the materials enable it to run into worry by application of tensile forces. A ductile material must be both strong and plastics. The ductility is usually measured in terms the percentage of elongation and the percentage of the reduction in area. The ductility commonly used in the engineering practice in order to diminish the ductility in or mild steel, copper, aluminum, nickel and zinc and tins. So friends, I want to tell you here that the ductility, if suppose the material is there, if you apply the tensile forces, due to this one, it will be very elongated like a varies. And if you remove the load, it will not come back to original position shape. So it is both enough in tensile strength, should be enough strength, and also it should be good plasticity. So plasticity means it should not come back. So you have to make the worry by application of the tensile forces. You remember that ductility is the combination properties of the tensile strength. It should be the combined property tensile strength and also plasticity. Enough. This is two property. Ductility is the it is a property of the material to enable to draw into the worry by the application of the tensile forces. Understood? This is it should be good strength, tensile strength, and also plasticity. A ductile materials is the ability of the materials to draw in the worry with a help application of tensile forces. Ductile material both the strong, it is tensile strength is strong, and also plasticity should not come back. Measure in the, actually the how much ductility is there, it is a percentage of elongation. You know that percentage of elongation is a measure of the ductility. It is asking in the interview, how will ductility you can express the percentage of elongation. So percentage of elongation, you know, the final length minus original length by original length, or reduction of area, percentage of reduction of area, you know that original area minus final area by the original area, that is like that. If you remember that if elongation if more than 5%, then the material is called the ductility. If less than the 5% of the elongation, that is called the brittle materials. Okay. The aluminum, nickel, and zincs, these materials are the ductile materials. Okay. Yeah, just to see if this is one metal is there, this is one fixing point this side and this fixing point, and that is called grip. If you apply the loads, if in the directions, okay, what will happen if you fix in this and apply like that, it will be deformed. Okay, it will deform and like worries. So it is a combination application tensile stress plus plasticity, that is ductile by application of tensile. So you are making the worry. Worry is the property of the worry material is ductility. Okay. See, this worries you are using, you are making the property of the ductile copper worry you are using, right? Again, this is the terms. Okay. Term used in the plastic deformation occurs by result of applying the tensile loads. Ductility is combined property of the plasticity and tenacity. Tenacity is nothing but tensile stress, I already told. Ductility is combination property of tenacity. Tenacity, you know, that is called the tensile strength. Okay, tensile strength and plasticity. Okay, deform forces. Okay, that will save when deform the force is removed. You remove it will not come back. The example of worrying drawing and reducing the diameter by this one. Worry drawing, you are doing the worry drawings. This one. If you suppose this is the ductile materials, if you apply, this is the metals. If you apply loads like this, then what will happen? Thin worry you can get. You can read in the manufacturing technology. This worry drawing is the property of the ductile materials. Normally, the percentage of elongation is exceed 5% of the material, that is called ductile material. If percentage of elongation is less than 5%, that is called brittle material. Lead, copper, aluminum, mild steel are the typical example for the ductile materials. Okay. So malleability. Malleability is special case of the ductility which permit the materials to roll and hammer into the thin sheets. Okay. If this is a metal either, if you will hit, then it will become the thin sheets. Thin sheet. Okay, like the thin sheets. A special case by application of the compressive forces here. If you apply the compressive forces, there ductility you are applying the forces in ductility, tensile forces, but here you will apply the compressive forces. Then it will make the thin sheets. You can make the thin sheets. There is a worry here, thin. The special malleability is the ability of materials to enable to make the thin sheets by application of the compressive forces. Malleability should be, it should be plastic, but it is not necessary that it should be strong. So malleability also we can tell that it is a combination property of the compressive strength and plasticity. Okay. How the ductility is the combination of the tensile strength, the tenacity, and the plasticity. Here malleability we can write, it is a combination property of the compressive strength and plasticity. Because once it will be compressed to the sheet, thin sheet, if you remove the load, it should not come back to the original shape and side. The malleability, malleable material commonly used in engineering practice, that is the lead, soft steel and wrought irons, copper and aluminum, these are all are the malleable materials. So friends, see it is looks like that. If you hammer to the hammer by repetitive compressive stresses, it will become the thin sheet. Okay, it is hammered into the thin sheets. Malleability, the term used the plastic deformation occur by the resulting applying the compressive forces. That is the plastic deformation, the ductility is happening, the plastic deformation is happening are the result of the tensile loads. Here the compressive load, that is the different. The malleability materials combine the property of the plasticity and compressibility, so that it can be squeezed to shape the process of forging, rolling and riveting heads, that is the malleability. So the property used in the forgings, because in forging also you heating the materials to some temperatures, and after that you are applying the hammering, then it is become thin sheets, the forging. And also same the rivet joints, you are making the rivet head, that is also the property is called the malleability property is used. See this two plate is there, and this rivet you are putting and you are applying the compressive loads, then it will be forming the head. Okay. See the metal hammer into the thin sheets is the property is called malleability. It is suppose this is the metal, you are applying this hammering, then it is become the thin sheets. Gold is the most malleable materials. Okay, remember that. That's why you are making so many ornamentals. Okay, so gold is the most malleable materials. Comparison between ductility and malleability, already you know ductility frequently used interchangeably, but it is not that. Ductility is a tensile quality, but where the malleability is the compressive quality, and both are the plasticity there. So remember that the ductility is the ability of materials to don't vary by application of tensile force. Malleability, it is making to the thin sheets by hammering action by the application of the compressive forces. So malleability is the compressive quality. Ductile material should be tensile strength should be high, and the malleability property, the compressive strength will be high. So what is the brittleness? Brittleness, it is the reverse of ductility. What is the ductility? It will by application of the loads, it will elongate it. Okay, tensile loads. It is the property of the material by opposite to ductility, and it is properties by breaking the material without little permanent destructions. So what is happening? The ductility, this is mild steel is the ductility materials. The stress and strain diagrams you will see that is it is a fail. It shows that it is more ductility, and it is giving the appreciable deformation before the failures. But if you see the brittle material stress and strain diagram like cast iron, it is going and fail. So without permanent deformation, no permanent deformation. With little, we can tell there is a little deformations of the materials. Okay, before fractures, before it is fracturing, very little deformations. It is a property of the breaking of the metal with a little permanent deformation is called brittleness. Material is subjected to tensile loads, snap without giving a sensible elongation. It will not, if you will apply the specimen in tensile, but the deformation is very small, but it will fail. So without noticeable deformation, the material will fail. That is called brittle material. Cast iron is more brittle. It is a brittle material. Cast iron is a more brittle material. If you will see the stress and strain diagram of mild steel, deformation is high. Okay, but if you see the brittle material, it will be appreciable, less deformation will fail. So if you will compare the stress and strain diagrams of these materials. So see, this is the brittle materials, the stress and strain diagram is like that, but it is a ductile material, the stress and the deformation is more here. So ductile material, this is brittle material, with deformation is very small. Okay, the brittle material failure is like that. Okay. But in ductile material failure is cup and cone type failures. Okay, but here sudden failure 90 degree to the applied loads. What is the toughness? It is the property of material to resist the fractures. Due to the high impact loads like hammering. The property of the materials to resist the fractures due to the high impact load like hammering, hammer blows. So it is the high impact loads. If suppose one metal is there, one high impact with certain velocity will apply the loads, it should not be fail. That is called toughness of the materials, and we will tell that how we are doing. Toughness of the material decreases when it is heated, and toughness is the ability of materials to resist the fracture due to the high impact load, that is called toughness. The toughness is the material decrease when it is heated. If heating, the toughness will decrease. It will measure the amount of energy for unit volume of the material observed up to the fracture points. So friends, toughness you can tell, suppose this is the stress and strain diagrams, you are familiar. It is the amount of energy observed per unit volume of the materials up to the fracture. This is fracture point. This entire things we are telling this is called the toughness. A property of the desired part subject to a shock and impact loads. When the material is subjected to the shock and impact, that time the toughness of material should be high. It will be high. Okay. So that is called the toughness. That is called the toughness of the metals. Okay. So you know that also strain energy resilience, the amount of energy observed of the materials up to the elastic limit. That is called, this is called the resilience. The amount of energy observed by materials up to elastic limit, that is called resilience. The amount of, this is called the resilience. The amount of materials observed up to the fractures, okay, that is called the toughness. That is the difference between toughness and this is toughness. Okay, it is the property of materials to resist the fracture due to the high impact load. Like this is called the like hammer blow, that is called toughness. See, this is hammer. This is the metal is bending, but it is not failing. This is we are using the ISO test and Charpik test. You maybe ISO and Charpik test is used to measure the toughness of materials. So if the tensile stress and this is the tensile strain, if you see the area of more area which is covering, that is more tough materials. If you see here the area covering, suppose this is A, this is B, this is C, the area covered by the B metal is high, so is high, more tough materials. But if you see the area covered by the A metal, the smaller toughness but high strength, strength is high, tensile strength is high but it is less, but it is less area is covering, so it is low toughness. You can very small toughness, but it is high toughness. Just second. So the machinability, it is the property of the material which refer to the relative case with which the material can be cut. Machinability means it is easy to cut a material. If suppose it is easy to cut, then that is good machinability. So the machine of the materials can measure the number of ways, such as comparing the two life of the cutting of different material or thrust required to remove the material at some given rate of energy. It required to remove the unit volume of materials. It may be noted that the brass can be easily machined than the steel. So machinability, it is the index, machinability is the index of the tool lives. If tool life of material will be tool life will increases, means the machinability, which machining you are doing, which material machining, that is easy to machine, that's why tool life of material is increasing. Okay, the property of material which reflect the easiness of the material. If material is easy to cut, then we tell good machinability is there. Example, with the brass materials is very soft, you can cut, you can easily machine than the steel. See, it is machinability used in the machining industries. Okay, okay. You just see here the machinability, the materials. Okay, it is if easy machining. If easy machining is doing, then we can tell that this machinability of the material is good, and the tool life of material will be increases. What is the resilience? Already I told the resilience is a property of material to absorb the energy and to resist the shock and the impact loads. This one. Okay friends, so resilience is the property of materials to absorb the energy and to resist the shock and the impact loads. It measures the amount of energy observed per the unit volume within the elastic limit, that is called the resilience. Okay. energy per unit volume, that is called the resilience. The property is essential for the spring materials. So this resilience, if you will make the stress and strain diagrams of this one, the energy observes up to elasticity, then that is called the resilience. Okay, stress and strain diagrams if you make, okay, the amount of energy observed per unit volume within elastic limit is known as resilience, or we can know that is called the proof resilience. We are taking that. Okay, toughness, it is the amount of per unit volume we are taking the modulus of resilience. If you are taking the unit volume, then that is called, suppose if you make the P and the del force and deflection diagrams, it will be like that. Means P and deflection diagram, it will give the energy absorption per unit volume in stress and strain, that is giving the modulus of resilience. If you are that is going modulus of resilience in unit volume. So if you take the up to fractures, then the energy observed up to the fracture point, that is called toughness. Okay. Next, it is coming the creep. What is the creep? When a part is subjected to a constant stresses at a high temperature for a long period of time, it will go the slow and permanent deformation is known as a creep. Creep is a slow and progressive deformation of the material by virtue of the constant load at a long period of time at elevated temperature, then that is called the creep. This is depending upon the temperatures. If temperature is high, then the creep will be high. Usually at elevated temperature means it is the temperature which is T by 3 is greater than T by 3, T is the melting point of temperature by T by 3. If you greater, then that is called the elevated temperature. So elevated temperature T, suppose elevated temperature is equal to T by 3. So T is equal to the melting point of temperatures. This property is melting point of temperature divided by 3, that is called elevated temperature. The property is considered in designing of internal combustion engine, boiler and turbine. This property is considered in designing of the internal combustion engine, since the internal combustion engine is exposed that temperatures, high temperature is applied, and over a period of time, and that also stress is subjected to. Then in that condition, the creep is important when you are designing the internal combustion engine or boilers. Boilers is also subjected to the temperatures and stresses, okay, and turbine, and that is the property of the material is should good with creep. Okay, remember that the slow and progressive deformation of the material by application of the load over a long period of time above that elevated temperature, that is the property is called the creep. Creep is depending upon the temperature and usually at elevated temperatures. It is high. It is the slow and the progressive deformation of the material with a constant stress is known as stresses. Depending on temperature, stress below which the limit is called permanent deformation. This is most generally defined the time dependent strain occurring in this one. How will do the creep test? So what you suppose this is one chamber is there, you put this specimen inside the chamber and apply the loads, okay, and you heat, then you apply the loads, then you can know the strain, and with respect to time it will come, this graph is like that. So there is just 3 stages you will get, 1, 2, 3. At instantly you will get some strain, and it will strain rate will be decrease, again it will be in constant, then again it will strain will decrease. So 1 to 2 we are taking, this is good time period of the creep, and you will study later in that. Just now slow and progressive deformation of the metal with a constant time stresses is known as constant stress is known as a creep. What is the fatigue? When a material is sometimes what will the material is subjected to repeated stresses, it fail at a stress below the yield point stresses. Such type of failure is known as a fatigue. So you know that if a material if a load like this it will fail it will fail at a yield point, but if you apply the loads, repeatable state means compressive and stress, one time compressive stress, one time tensile stresses, okay, one time compressive stresses, one time tension stresses. Repeatably you will apply the loads like this, cycling loads you will apply. It will fail below, suppose the yield strength is 100, but it will fail at a stress of, suppose one stress will 50 MPa, it will fail at 50 MPa. When material is subjected to repeated stress, it will fail a stress below the yield point stresses. Such type of failure is known as fatigue. The failure is caused by means of progressive crack formation, which is usually fine and microscopic size. The failure is due to the formation of crack and the surface, and it will propagate. The microscopic. This property is considered designing of shaft connecting rods and spring and gear. This is all the fatigue loads, because in spring it is reverse loads, load tension and compress is acting, so it will fail at stress below the yield point stresses, that is called the fatigue stresses. Okay, it is a gear, spring, these are gears and the spring connecting rods. When you are designing, you have to take the fatigue in consideration. So friends, what is the hardness? Hardness, it is the property of the materials to enable to resist the permanent deformation or penetration or indentations. Actually, if when you will petrol hard, suppose this is a one metal pieces, if it will scratch like this one, scriber it will scratch, it will resist the deformation or penetration, and then that is, we will tell this property is called the hardness. The size of the indentation by various type of indenter, the measure of hardness, Brinell hardness test, Rockwell hardness test, and Beaker hardness test or diamond pyramids test are used to measure the hardness. This test will give the hardness related to the yield pressure. Okay, this will give the unit of Newton per mm square or Newton MPa, like that. So hardness is the ability of materials to resist the permanent deformation or that is penetration. If suppose this is a metal, at height the ball if will drop like this, then the impression it will come to the impression will come to these metals. If less impression, then is good hardness. If more impression, there is less hardness. So just to see, this is the ability of the metals to withstand the scratch, absorption, indation by another hard body. It can indication the wear resistance of metal. Suppose if this is a metal either, suppose this is hard ball either, you apply the loads like this. This is some small impression is coming. A small impression is coming to here. Okay, if hard metal, the small impression will come to here. If it is softer metal, the greater impression, so it will impression will be like this. So it will be softer metal, but in hard metal what will come? Less impressions. Okay, this is a hardness test. Thank you very much. Now we completed chapter number 1 at the end, and this is just a long took the time to complete all property of the materials. So friends, I think you understood. You go your home, make the notes, and this completed here mechanical property of the materials. Next chapters, next we will start the new chapters. Thank you very much for your patience.